All right, let's have a look here real quick. Okay, so like I say, today kind of the plan is let's go ahead and put phones away and just, well, this will probably be pretty brief. I'd like to give you a little time to either finish up the test or if you're done with that, you can, there'll be an assignment up for this. The assignment is really, I mean, this is very introductory. There's not a lot of math going on. It's more just sort of talking about the definitions of what we're gonna talk about this chapter, kind of getting some vocabulary straight, things like that. Then we'll sort of jump into more of the math in the next section. This is pretty lightweight introductory stuff. Okay, so we're gonna, in this, oh, that's a little loud. Wow. So we're talking about polygons. What this chapter is mostly about, it would be a certain type of polygon. We're talking about quadrilaterals. But we're going to come back later on in the year and look at other types of polygons also. So we'll briefly look at just what the definition of a polygon is and how do we name them and classify them and things like that. So the objectives, we just want to be able to identify, name, and describe polygons. The part that's, if there's anything on here, you're going to have to probably think about it a little bit and maybe make a few flashcards. It's going to be naming the different kinds of polygons based on the number of sides. Everything else, I think, will be largely review, pretty straightforward, pretty simple. We want to know how to calculate the sum of the measures of the interior angles of a polygon, any kind of polygon, specifically quadrilaterals we'll work with a lot. So what are the definitions? A polygon, it's just a shape, okay, but it's a specific kind of shape. We're talking about two-dimensional shapes that we can draw on a flat surface, right? We actually will look later on in the year at some three-dimensional shapes, but this is still two-dimensional stuff. It's formed by at least three segments, three or more segments. They all have to be straight. They're line segments, so you can't have any curvature to any of them. And there's a bunch of ways you could define this, but the way our book does, and this works, would be to say that no two of the sides have a common endpoint and are collinear at the same time, right? So in other words, if I were to take this picture up here of a polygon, right? This one has 5 sides. If I were to put another vertex right there, that really wouldn't make sense, would it? No. It didn't change the shape at all, did it? No. Right? So that wouldn't make it a 6-sided figure. It's still just a 5-sided figure because these two segments, right there and right there, are collinear, right? They sit on the same line. And so, therefore, that is not considered to be a vertex. It's not an endpoint of a segment. Does that make sense? Yes. So there has to be, the segments, the endpoints have to make sense in a way, right? They have to make sense in that they have to describe a place where the sides turn from one another at least a little bit, right? They can't form a straight angle. Can't be collinear. Okay, each of these sides has to intersect exactly 2 other sides. So notice up here in this polygon that each of these vertices only connects 2 sides, right? You can't connect more than 2 sides. If so, it becomes a weird shape and it's not classified as a polygon. A vertex is defined as an endpoint of a side, which plural is vertices. You can name a polygon by listing its vertices, but you have to do it consecutively. So if we're going to name this polygon up here, what is a name that would work? Abel, what's a name that would work for that polygon if I'm just going to label the vertices consecutively?
STPQR.
STPQR, good. So he started at S and walked around the outside clockwise. And that's fine. Could he have gone the other way? Sure. You can start at any point and move around the outside to label the vertices consecutively in any order. But give me an example of one that doesn't work. Janae, what's an example of a name for this that would not work?
TS.
Yeah, good. Because she skipped around, right? She started at R and then she jumped over to T. You can't do that. It has to be consecutive. Okay? So when you're given information, and on some problems, in this chapter, you're going to be given some information and you're going to have to draw the polygon in your notebook to kind of reference, but it's not going to give you a picture. So if it says that, for example, later on in the chapter we're talking about parallelogram, which we haven't talked about yet, but we will. Parallelogram, A, B, C, D. We know that that's the order in which those vertices are going to appear consecutively around the outside. Does that make sense? It really wouldn't matter which direction you went to draw your polygon. Either way would work, but they have to be consecutive. Okay, so real quick, let's take a look here. So, which of these, let's go through these one at a time. Decide whether these are polygons or not, based on our description. Okay. Leave it away there a little bit, didn't I? Okay, so Walter, is A a polygon?
No.
How come? What would be your reason? So it is. It's weird looking, and we're gonna classify it in a certain way, but it is a polygon. You're right, because it's got 4 sides. Each of the sides are straight, and each vertex only connects to 2 sides, right? Connects to exactly 2 sides. Okay, Gina, is B a polygon?
Yes.
It is. Good. Fits the bill, doesn't it? Vanessa, how about C? This guy right here. What's wrong with it? How many sides does it have? 5. Is each side straight? Okay, check. Does each vertex connect to exactly 2 sides? So it's okay. It fits the bill, doesn't it? Okay, how about D? Mallory, how about D? What's wrong? Yeah, it's got a curved side. It's out. What about E? Kara, you're shaking your head. How come?
It doesn't connect to it.
Okay, it doesn't connect. So this vertex right here connects to how many sides? 1. How many does it have to connect to? 2. Okay, so it's out. What about F? That looks good, doesn't it, Amon? What do you think?
I think it is.
Okay, think it is?
Yeah.
What do you think, Sean? You want to dispute that? You think F's okay?
I don't.
Not sure? What do you think, Emilio? What do you think? No, how can you say no? Okay, here's the problem. Yeah, there's a problem because, look, right here, that point right there is where some sides intersect, so it must be a vertex, right? That's what vertices are, but it connects to 4, not 2. So that's out, right? It's no good. Okay. Questions? Here's how we name these things. Oops. All right, I don't think this is the most important thing in the world, but you need to have some, I mean, when it gets beyond really large numbers of sides, I don't remember what they're called, honestly. I barely remember these. In math, like in college, for example, we probably wouldn't have ever called a 7-sided polygon a heptagon. We would have called it a 7gon, seriously. Because it's not really that crucial that you get the specific name. But for some reason, in high school, even on the Smarter Balance test, this is something that could come up. So you just got to be aware of these. So 3-sided, we already know, that's a triangle. 4-sided is a quadrilateral. That's going to stick in your head for sure because that's what we deal with all chapter. Pentagon, 5-sided. Hexagon, 6-sided. Heptagon, 7-sided. These are in the book. 8-sided is an octagon, 9-sided is a nonagon, 10-sided is a decagon, and 12-sided is a dodecagon. And those are just the ones that you would typically maybe run into. Bigger than that, we don't ever really try to worry about naming them. Yep. What's a what? Oh, okay, so an n-sided is just an n-gon. So what that means is in general, the n could have any number, any integer number, right, or any whole number, 3 or greater. So if it's an 11-sided polygon, we could call it, if n is 11, because that's the number of sides, we could call it an 11-gon. If n is 5, we could call it a 5-gon, right? I mean, that works, okay? Where the gon just tells us that it's some kind of polygon, and the number indicates obviously the number of sides. So that's that. Okay, so convex or concave. Walter identified kind of a strange looking polygon just a few minutes ago. It was one where one of the points was sort of indented towards the interior of the polygon. This is one way that we can classify polygons. We can classify them as being convex if there are no dents in them, so to speak. The mathematical way of describing that would say if no line containing a side ever passes through the interior of the polygon, then it's convex. Okay? However, if there is a dent, then it's concave. Think of it as like a cave, right? There's a cave in the terrain here on this polygon, right? It's been caved in. How do we know mathematically? Because that doesn't sound very mathematical to say it's been dented in, right? That's probably not how a mathematician would refer to this. In mathematics, we want to have some kind of an explanation that is, that's not open for interpretation. It's just very straightforward, testable, dry, and mathematical, right? So to test for concavity of a polygon, we just have to see if we can draw a line containing a side that passes through the interior of the polygon, right? If that can happen, it's concave. Like for example, if we take this side right here, take the purple side, and we extend that and make a line out of it, clearly that line is passing through points on the interior of the polygon, so it's concave. Yes?
You should do the one that.
Yeah, or you could do this one right here also. Yeah. If you can do one, you're always guaranteed to be able to do two, at least, maybe more. Okay. But if, all you have to do is see if you can find that you can do one, that's enough. You know it's concave. Okay, so convex or concave? Concave. Convex or concave? Convex, there you go, yeah. And you might see those words, not that this is really related to geometry, but those are words that if you end up studying physical science, either in high school or beyond, these are words that apply to lenses too. Like if you talk about a convex lens would be a lens. Imagine you take the lens out of some glasses and then you turn it sideways. A convex lens, when you turn it sideways, would have a profile like that. Okay. A concave lens, if you were to turn it sideways and like cut it through the middle, it would look like that. So the lens would be thicker at the edges and thinner in the middle. Does that make sense? Okay. And they have different optical properties that we'll talk about in physics someday when you take a physics class. Okay, so a polygon is equilateral, just like we've talked about triangles. It's equilateral if all of the sides are congruent. It's equiangular if all of the angles are congruent, and it's regular if it's both of these at the same time. Okay, it has to be both equilateral and equiangular to be regular. So, what do you think about this guy right here? I mean, don't look at the red. Test yourself a little bit. I won't color it out. Just resist the temptation. Do you think that's equilateral, equiangular, or both? Is it equilateral? How do we know? Yeah, because we have all these congruence marks, right? Even if it doesn't look like it, it's telling us by those congruence marks that all the sides are congruent and therefore have the same length. So it is equilateral, for sure. Is it equiangular? No way, right? it's not. It doesn't look like it at all, but we don't have any marks to indicate that it is, even if it did look like it, right? What about this guy right here? Is it equilateral? What do you think, Sierra? Is that one equilateral?
What?
Is this polygon right here equilateral?
Yes.
Okay, why? Tell me why. Equilateral means all the sides are the same length, right?
Yeah.
So we're looking at this one right there. How many sides does it have?
All of them have to be equal?
All of them have to be the same length, right?
So we can't put the two sides on.
Okay, yeah, because they're not, because I have, these two sides are congruent to each other, and those two are congruent to each other, but these two are not congruent to each other. So it's not equilateral, good. Is it equiangular? Equa meaning same, angular meaning all the angles. Are the angles all the same? Yeah, they're all right angles, aren't they? So they're all congruent. So it is equiangular. Yeah, I know it does, but just ignore the red. How about this guy right here? Don't cheat, don't look. What do you think? What do you think about that? Savannah? Equilateral? Equiangular? Nope, opposite angles are not. And then finally, how about this guy? Yeah, it's regular, isn't it? Because it's both equilateral and equiangular. Okay. All right. Notice that regular polygons have lots of symmetry. We'll talk more about symmetry later, right? But they look, you could turn it and it would look the same. You could reflect it, right? Okay, so diagonals are just defined as being segments that join non-consecutive vertices. Okay, so it's a diagonal if it joins a vertex to another vertex that it's not next to, right? Does that make sense? Okay. Interior angles. Now I want to look at this one. Let's go back. How many? That's what is that? What's that called? What is that shape called? Angelica, what do you think? Pentagon, good, 5 sides, yeah. So what's the sum of the interior angles of a triangle?
180.
180, okay. So the question I've got for you now is, can we come up with a scheme for finding the sum of all the interior angles of polygons other than triangles? Anybody want to hazard a guess as to what the sum of all the interior angles would be in this shape? Say it again.
180 plus 180 plus 180.
Yeah, how'd you get that?
Because there's 3 triangles within it.
Yeah. Okay, look, we can divide this up into 3 separate triangles, can't we? Right? Let's look at the sums of the interior angles of each of those. So this one, we know that that angle plus that angle plus that angle is 180, right? Okay, but over here, let's make these green. This one's going to also include this angle right there, and the green plus the purple would make that whole interior angle of the polygon, wouldn't it? So all the greens combined make another 180, right? And then over here, these orange angles, if I look at all 3 of those combined, that makes the whole interior angle for the polygon, right? This guy is okay by itself, but the green and the orange there complete that whole interior angle, right? So does it make sense then that really we could find out what the sum of the interior angles of the complex, weird-looking polygon are by just adding up the interior angles of all of the triangles that make it up? Okay, so 180 plus 180 plus 180 is
540.
540. Very good. So we get 540 degrees of interior angle space inside this polygon. Can we come up with a pattern here? Let's see if we can see a pattern. So I'm going to make some shapes. Let's see. Let's do. So there's 4 sides. Let's see. I won't probably get them all, but we'll get some of them. This guy's good. I think that's about the most I can do. Yeah, that's enough. So let's divide these up into triangles. How many? Two triangles, and so we're gonna get 2 times 180 degrees. Agreed? Okay, how about here? 5 sides. How many triangles? 3. Okay. Here we've got 6 sides. 4 triangles. Do you see a pattern? A 4-sided shape divides into 2 triangles. A 5-sided shape divides into 3 triangles. A 6-sided shape divides into 4 triangles. Savannah, how many triangles do you think I could carve out of a 9-sided shape? What do you think?
I don't know.
Anybody see a pattern?
6.
What do you think?
So it's subtracting 2 in each one, right?
Yeah. Everybody see that? Okay, everybody see that? In each case, if I have a 4-sided shape, it gave us 2 triangles. 5-sided shape gave us 3. 6-sided shape gave us 4. And we could keep going with that pattern. And there's always going to be 2 fewer triangles than there are sides. Okay, why do you suppose there's 2 fewer sides than there are triangles? Well, because I've got 2 vertices here that I can't use to make triangles, right? Because those are, does that make sense? I can only create triangles by adding diagonals, and diagonals can only be formed by looking at non-consecutive vertices, right? So I'm always going to skip 2, because those are the ones that are next to the vertex, right? So we can come up with a formula then. How, you see if you can complete this. So the sum of the interior angles for an n-gon. And what's an n-gon mean again?
Any number, like a polygon.
Okay, it's a polygon with how many sides?
Any side, like 5.
Okay, and what's, if I write it this way, what's the symbol that represents the number of sides? N. So it's got n sides. An n-gon has n sides. What is n? Well, you pick. You could pick n to be anything, but it's a variable, right? We can let it be whatever we want it to be. Let's leave it general though, because in math, when things are general, they're powerful. If they're general, then we haven't pinned anything down and we can use it in more cases, right? So what do you think? What's going to be the area, the sum of all the interior angles for an n-gon? So let's just call that a sub n equals what? What's our formula going to do? If I wanted to calculate the total interior angle space here, the sum of all the interior angles, what would I do? Drew told us. What was the strategy? 180 plus 180 plus 180, or in other words, 180 times 3. Here it would have been 180 times 2, because they're 2 triangles. Here it would have been 180 times 4. So in general, if I've got n sides on a polygon, what do you think? Do you have an idea, Savannah? I'm going to multiply 180 times something, but what am I going to multiply 180 times? If it's got n sides in the polygon, how many triangles? If n is 11, how many would there be? 9, right? Just always 2 less, isn't it? Right? 4 sides gave us 2 triangles, 6 sides gave us 4 triangles. Continue that pattern. If we had 100 sides, how many triangles?
98.
Okay. So what if we had n sides? How many triangles? That's weird, isn't it? That's what we do in math a lot. We try to define things in terms. We don't want to pin it down to one specific number of sides, because then we're stuck with it. We want to make it general. What's it going to be? What do you think? I have n sides. Alexi, what do you think? You got an idea? D? Help us out. we have n sides in a triangle, or n sides in a polygon, how many triangles is that gonna carve into? What if I have 19? How many sides? I mean 19 sides, how many triangles? 17, how'd you get that? Subtract 2, yeah, that's right. So what if I have 101?
99.
Okay, what if I have n?
0, 1.
No, it wouldn't be n. If I have n sides,
Okay,
how many
1.
triangles? What about the 2? But not 2 total,
Negative.
just 2 less, isn't it? How would I say that? How do we say 2 less in math? Or minus 2, right? So what's it gonna be? If I have n sides, how many triangles?
Negative 2. Negative 1. Negative 1.
I wish somebody would get this. This would be cool if somebody would get that. Okay, so I'll let Kevin. So what I'm looking at is whatever n is, 2 less than that is just n minus 2, right? So the sum of the interior angles for an n-sided polygon is just n minus 2, whatever that number is, times 180, right? Okay, so if we want to add up, we don't have to do this, but if we wanted to add up the sum of the interior angles for a 17-gon, whatever the heck you'd call that, it's just going to equal what times 180? Yeah, so n is 17, so what's that going to be? 17 minus 2, I bet you know that. 15 times 180, right? Get the idea? Okay. All right. That might seem kind of weird, but and I'm sure that was kind of probably annoying to you. That was just not. But that's this is something. Trust me, for somebody that has studied a lot of math, and I teach calculus, this is the kind of thinking that you're going to do in math from here on out. I mean, this is algebraic thinking, right? Where we want to represent something by a symbol so it retains all its generality. It's not pinned down to be specific. So that's actually a pretty interesting and important concept going forward in math. All right. Oops. Yeah. How much time we got? If we have a little time here, wait till I'm done, and then absolutely.
This is real quick. We got 14 minutes.
What's my degree? My degree's in physics.
We got 14 minutes.
14 minutes. Okay. Good.
Who's teaching algebra 2?
Usually I teach algebra 2. Usually I teach honors, and I teach algebra 2. Usually, I mean, this is one year that I'm teaching geometry. Okay, so okay, so we did all that. Okay, how would we do this? How would we go about this? Ruby, how would we go about this, do you think? How would I go about this if I want to solve for x? P, Q, R. Okay, now that's interesting. If I form a triangle, I like the thinking, but I want somebody to maybe tell me what the problem with that is. It's a good idea, but if I carve this into a triangle, I know that that one's x, don't I? So what's the problem? Yeah, how do I know? I know that this whole angle is 80, but do I know what that little angle would be? I don't, right? It might be 40, but it might not too, right? Probably isn't. So we can't really set up a relationship there to solve for x, right? We have to be able to come up with some geometry relationship that we know is going to be true that involves some x's so we can shift into algebra mode and solve for x. Are you kind of starting to, I mean, it's as we move through this stuff in the year, you're kind of starting to see here that if you think about this in terms of a strategy, we just have to be able to get an equation that only has x's in it, and we should be fine. Then we can solve for it. Add like terms, isolate x. What do you think?
Would you do like A or equals 1 minus 2?
Okay, so So we could determine, how many sides are there in this polygon? 4. So then what's the sum of the interior angles? 360, right? 4 minus 2 is 2 triangles, so 2 times 180 is 360, right? So if we know that all of the angles add up to 360, then that gives me a relationship where I can come up with an algebra equation, right? That just tells me that 80 plus 70 plus x plus 2x equals 360, right? And that's something I can solve, right? I would just combine like terms and, isolate the x, and I've got it, right? And you can all do that. I won't even take you through that. I know everybody can do that if you got good at algebra.
And what is this?
What do you mean?
And what is that?
How did you know there were 360 degrees in it?
No, I mean like the whole A and X.
Okay, because how many sides are there on this? 4. So what do all the angles add up to? 4 minus 2 times 180. See what I'm saying? That's what that's for. It's just a relationship. What if this polygon had like 6 sides, and we knew we had an expression for each side? Does that make sense? Or each angle? See where that comes from. In order to be able to set up the geometry equation, we have to know what all of those angles add up to. Okay. Oops. Okay, so here's what it would look like, right? We had combined like terms, x plus 2x is 3x, 70 and 80 is 150. Subtract the 150, divide by 3, and we got it. We got 70. Okay. How could we check? Plug them in and see that they all add up to 360, right? All right, good enough. Okay. Yes?
Can you hear questions for today?
Yes, let me do that first. We got a few minutes. I've got Chromebooks if anybody wants to jump on and work on a problem or two on the test. Monday we'll have a lab day. I'll put this assignment up. Yes.
So to remind you at the end of the class.
Thank you. I'll do that right now. You got it. Perfect.
I didn't guess anything, so.
That's a word.
Dude, so I didn't guess anything, so.
Can you request me?
I can't.
Just right if you request me to.
You betcha. Okay, real quick, just raise your hand if you want to be requested. Make sure I get everybody that wants to be. Okay, leave them up for a second. Sam, gotcha. Let's see. Nick, gotcha. This thing is slow. Drew, gotcha. Savannah, gotcha. Okay. Ruby, gotcha. And then Danae and Ahmad, gotcha. Perfect. Anybody want me to grab a Chromebook for them?
I think it would be. Next time we
Well, you have both CE.
Okay, so let's see. We're gonna divide
No.
the class for a little weekend trivia throwdown here. See who gets bragging rights for the weekend. How about if we divide it today? Either way is not gonna be very fair. No, I'm gonna divide it right here today. You guys are gonna be shorthanded.
Oh.
That's all right. I have faith in you. Are you kidding me? Okay. No, I'm not kidding you. That's how we're doing it today.
Yeah, thank you.
But I don't myself.
Oh, sure you do.
It's just like anything to me, or it's not?
No, it's anything. Yeah, we did our math for the day. Now we're,
Yes.